So here is a YouTube video that is just a fun little music video about the TCA cycle, and you can go ahead and watch that. It's posted on Canvas. Okay, so the TCA cycle. So again, we have the common substrate of acetyl-CoA, and when it's oxidized in the TCA cycle, it generates carbon dioxide, reduced electron carriers. So remember, that's the NADH and the FADH2, and GTP. Now, when you see GTP, don't be afraid. If you don't know what that is, it's in some graphs it even shows it as just as ATP because it's energetically equivalent. However, it's in the step from succinyl-CoA, catalyzed by succinyl-CoA synthase. But the only difference is that GTP undergoes substrate level phosphorylation, so no oxygen is used, but it is a high energy phosphate bond that can be used for work. So again, you might see ATP sometimes, you might see a GTP sometimes. Okay, so the reduced electron carriers donate these electrons ultimately to oxygen via the electron transport chain, and that creates ATP. Now these cycles has lots of cofactors, co-substrates, and coenzymes that are needed in this. So there's a lot of input that's really needed to make this work well. So some of the cofactors are vitamin derived, such as thiamine or riboflavin. So if we have a deficiency of these, our TCA cycles may not work as well or at all. Okay, so on to oxidative phosphorylation. So the definition of oxidative phosphorylation is when electrons are captured from fuel oxidation and used to regenerate ATP. This requires electron donors. Well, actually, they're electron acceptors, and then they become electron donors. And it's in two simultaneous processes. So first, the substrate molecule undergoes oxidation to produce energy. Now, within this, electrons pass. Okay, so by the time the electron acceptor goes to the electron transport chain, it becomes an electron donor. And these electrons pass through a series of intermediate compounds, ultimately to oxygen, which is then reduced to water. Now, the compounds in this redox reaction constitute the respiratory chain, or the electron transport chain, and this occurs in the inner membrane of the mitochondria. Then there's phosphorylation of ADP, so we have the phosphate being added to the ADP to form ATP, using the energy from the electron transport chain. So oxidation of energy nutrients can occur through several reactions. So we think of when something is oxidized, of course, oxygen is added. But similarly, we can remove electrons or remove hydrogens to oxidize something. Now, oxidation is catalyzed by enzymes termed oxidoreductases. Now, for our conversation, the most important is these dehydrogenases, which remove hydrogens and electrons from the nutrient metabolites. So they oxidize them by removing the hydrogens and electrons. These hydrogens and electrons are then transferred to our co-substrate or enzyme, NAD/FAD, and hydrogens are moved, and they pass along the electron transport chain, causing a release in energy. Now, we also have the oxidases, but these are not used in the electron transport chain, and no energy is released. So as I said, the electron transport chain is located in the inner mitochondrial membrane. Electrons are donated by our electron first acceptors, then donors, pass through a series of electron carriers embedded in the membrane. And this creates energy derived from the redox reactions along the electron transport chain. Now, each component of the electron transport chain, S5, has the ability to donate and accept electrons. electrons released are used in part to form ATP. Now, the translocations of the protons, which we will get into if you're confused now, I will hopefully clear it up. Translocation of protons from the inner matrix of the mitochondria to the inner membrane space and back into the matrix provides energy. And this also forms ATP. Okay, so here each component of the electron transport chain is reduced as it accepts electrons and is oxidized as it passes the electrons down the chain. So there are five compartmentalized complexes in total, but 4 that catalyze the transfer of electrons through the chain. So first we have complex 1 and complex 2 that catalyze electron transfer to then CoQ from NADH and FADH2. So NADH is in complex 1, FADH2 is in complex 2. So in this stage in the electron transport chain, these co-substrates become electron donors and give the donors to these complexes. They flow through these complexes to CoQ. Then we go through CoQ, and this little arrow here, these black little arrows, indicate the transfer of electrons. So then the electrons go to complex 3, which then carry them to cytochrome C, and then all the electrons flow down and are reduced to oxygen and are reduced to H2O or water. Okay, so how does this work? How do they carry these electrons? Well, complex 1 and 2 have an iron-sulfur center that collects electrons, and hydrogen is released as protons. So let's go back to our picture for a quick second. So it collects the electrons in the iron-sulfur center and pumps the hydrogens from inside the matrix to the intramembrane space. So this is the inner membrane, and then the outer membrane would be out here. Okay, electrons are passed to the CoQ system, which regains the protons released at the iron center. And then after CoQ, it passes the electrons onto cytochromes. And these are also iron-containing electron-transferring proteins that carry electrons, but not protons. So hydrogens are reduced, CoQ are released as protons. There's no hydrogen transfer, again, in the cytochrome segment of the chain. The protons collected by CoQ are released into the mitochondrial matrix to form H2O. Now, cytochromes are heme proteins. They're iron-bound to porphyrin, and it's a similar molecule as hemoglobin. Now, the way that these iron-centered molecules accept and donate electrons is by changing their charge from a +2 to a +3. This should be a superscript, not a subscript. So it goes from +2 to a +3 plus an electron. And by transferring back and forth from these two, it can accept and donate electrons. Okay, so again, we have it in the electron transport chain in the inner mitochondrial membrane. And the components are situated in a way that it facilitates the uptake of electrons from the substrates to deliver oxygen. So they're sequential. So electrons pass from one, pass to the other, and it's very efficient. So energy to synthesize ATP in the electron transport chain comes from the translocation of protons. Okay, so we have these electron-accepting complexes that are kind of making the electrons flow, and this is a downhill energetic reaction. So as the electrons flow, they provide the energy needed to pump these hydrogens into this intermembrane space between the inner membrane and the outer membrane. And it this gradient where we have a positive charge on this inner membrane space, and it's highly acidic or more acidic because we have all these protons there. So the energy used from the downhill reactions of carrying electrons are used to pump hydrogen protons against the electrochemical gradient to create a concentration gradient in this intermembrane space. Now the membrane is impermeable to protons, so these cannot diffuse back across this lipid bilayer of the membrane. Now, because we have a high positive charge in this intermembrane space and less of a positive charge here, the hydrogen protons, the protons are attracted to the inner matrix, which is more negatively charged. So it really wants to diffuse back into the matrix, but can't because it's impermeable. Now, the way we get around this is that the protons go through complex 5, which is ATP synthase. And this is really an amazing complex. So this is the enzyme that ultimately generates ATP. It's a multi-enzyme unit. You can see it's very complicated. And this is the unit through which the protons are able to flow back into the matrix. And the protons, as the protons go through the ATP synthase, they turn this rotor and allow for ADP and the inorganic phosphate to bind back together to create ATP. So, as I said, the influx of protons turns the ATP synthase rotor. Then the ATP synthase releases the hydrogens back into the matrix. So we have, not only do we have ATP formed through the energy used from the protons going back through and turning that rotor, we also have a bunch of hydrogen protons back in the matrix. And again, here's a good YouTube video, and I will post that on the website. So let's call this part 2, and we'll have one more part.